Hello, I'm finding out about systems. Systems made simple. I hope. Here we go. What might the following have in common? Expedition to Mars, permanent bases on Moon and Mars, hospitals, energy, climate, international disaster relief, air traffic, airliners, helicopters, navies, satellites, high-speed rail transport, integrated rail rapid transit. One I wonder. Designed by systems architects and system designers, created by systems engineers. Well, of course, why didn't I think of that? So what are systems about? Hello. I've been finding out about systems. What people think they are and what they really might be. The woman in the street, the man on the train, seem to think that systems are something to do with computers. Persil, the people who make washing powder, declare that they have the ultimate washing system. Use their washing powder in their machine at the right temperature with the right water and you should get the whitest wash possible. Fair enough. Marvin, the paranoid android on Hitchhiker's Guide to the Galaxy, thinks the system is out to get him, whatever the system is. Pretty well everyone uses the term system, but they all seem to mean different things by it, which can be pretty confusing. Here's what people I met out and about thought about systems. That's technology that does something. Systems is an abstract concept used to manage complexity. Well, just about anything can be a system. No, it's a whole made up from interacting parts. It's a whole something complete. I don't know, except that systems can be either open or closed. The weather is a system. Listen to the forecast. There's a weather system out to the east bringing cold winds from the Urals. So, nothing to do with computers then. Systems are connected with ideas of emergence. Emergence, isn't that Aristotle, the ancient Greek? The whole is greater than the sum of the parts. Emergence, the classic example of emergence is self-awareness emerging from the human brain and from a passing student. A system is a complex whole made up of many interacting parts, and there are lots of systems. Let me see now. There are mountains, railways, nervous systems, solar, digestive, political, transport, education, economic, ecological, social systems, organisms, and so on. Societies behave like organisms. Thanks. That's quite enough to be getting on with, thank you. So, there you have it. Some people have no idea about systems or emergence, while some people think systems are computers, and some folks think systems are whole somethings made up of interacting parts with emergent properties of the whole. That's Aristotle's the whole is greater than the sum of the parts idea. Well, at least that identifies key systems ideas: parts, interactions, emergence, and complete wholes. Back to you, Derek. Thank you for that riveting stuff, and I hope you enjoy the Luxor Temple. Emergence. It all started back in 1912. A German scientist was watching a rotating lantern, one of those illuminated in the middle, which showed successive pictures of a horse. These were still pictures, but it appeared as though the horse was galloping. And the scientist asks the silly, simple question, where does the actual motion come from? Then there were people looking at flowers, and they were trying to work out where a rose flower came from. They imagined that there might be a tiny, tiny miniature rose inside a seed. And they discovered there wasn't. So where does the rose flower actually emerge from? Nowadays, of course, we all know about DNA. But that's not so obvious as it might appear. DNA is an inert chemical molecule, beg your pardon. So how can the universal blueprint of life be inert and dead? Where does life emerge from? And then there was the idea of Gestalt. This was a whole movement, particularly in Germany. And you can see from the picture the idea. If you look at parts of that picture, you've got no idea about the whole. It's only when you look at the whole picture that you can see a Dalmatian dog sniffing the ground. Something about the whole, which is not evident when you only look in the parts. So what is a system? Well, it's harder than you might think, but it's simpler too. A system is a whole something, as our student friend thought. It's complete, it's working, it's functional, it's operational. So are you a system? Humans are complex, sophisticated, adaptable, individual systems. Working together they form capable teams, and these are people systems. So looking at the movie there, is there a system in there? At what point do the parts become a system? And how do you know? Well, there certainly looks to be a degree of completeness. But is that all it takes to be a system? There are many kinds of systems: gambling, process and product, and so on. Nature is observed to only make whole systems, and that is actually called holism, which perhaps ought to be spelt with a W but isn't. And whole systems include people, molecules, cells, swarms, hives, shoals. And people also make wholes, man-made systems: civilizations, societies, automobiles, aircraft, ships, and so on. And there we have a row of fighter aircraft from the 60s. The Lightning. It was built using a thing called the Total Weapon System concept. But is the fighter a whole without a pilot in it? Can it actually do anything, or does it just sit, as are these, on the tarmac, leaking oil onto the concrete runway? Our student friend mentioned systems being opened or closed. A closed system has a boundary through which nothing can penetrate, while an open system exchanges energy, substance and information with its environment. So is the solar system abstract, illusory, conceptual? Is it open or is it closed? Is it boundful? Is it purposeful? Is a person a system? A team? A family? Is a human cell a system? Is a human cell open or closed? So a system is a whole something, complete, comprised of connected, interconnecting parts, therefore internally dynamic. A system is open, with throughputs of substance, energy and information. So linked processes can be suggested from inflow to outflow. It stabilizes dynamically, if at all, at high energy levels, and part of some greater, wider whole containing other interacting systems. Observation there: if a system were truly closed, how would we even know of its existence? Which brings to mind black holes. Then there's systems within systems within systems. Here we see the classic poached egg diagram. And here we can see a system of interest with subsystems inside it, and they are intraconnected. This system of interest sits inside an operating environment in which there are other sibling systems, and they all sit together inside a containing system, which is in itself connected to other containing systems through some external environment. So we have a hierarchy. If we alter a subsystem or an intraconnection, it will affect other subsystems, the system of interest, therefore the siblings, and therefore the whole containing system. Change a sibling, that will affect the system of interest and the contained subsystems. So you can have reverberations and you can have behavior. Now, using this sort of containment idea, we can think about schools containing departments, departments containing teams, teams containing teachers, or a company contains divisions, divisions contain groups, groups contain sections, sections contain teams, teams contain people. Public transport system, land, sea and air, rail and roads, air travel and shipping. Railways comprise stations, trains, rail systems, signalling systems. Roads carry buses, taxis and cars, bicycles and pedestrians, and so on. Simply organising and perceiving a problem or situation in this way makes things simpler, easier to understand, and it helps to see the whole picture, or as some people prefer to call it, the big picture. Now, here is a model which can represent an awful lot of things. It could represent, for example, a human with an alimentary canal going through the middle, taking in food and substance, being processed by various organic subsystems within the body, and something coming out. We don't want to go into that. But it could also represent a multicellular organism, or a factory with goods inwards, products out, or a school with students in and learned students out, and so on. In fact, this open systems model can be applied in principle to a large number of different things. And that's useful. One open system model fits very many different real-world systems. Open systems interconnect one with another. So this system model would interconnect with several other models. And the outflows from one become the inflows to the other, stimulating systems behaviour. Very different real-world systems may behave in the same way, however, giving you behavioural isomorphs. For example, different systems will have the same kind of transport systems in them. Supermarket queues, football queues, theatre queues, aircraft landing queues at an airport, surgeons' hospital queues, etc. Queues appear in all sorts of places, between systems and within systems. And all queues, no matter how different they are, and no matter what it is that's queuing, behave in much the same way. This helps us to understand and analyse. Then there are oscillating systems, and SHM stands, as you know, for simple harmonic motion. And that applies to musical instruments, sea waves, radio waves, cyclotrons, populations, sunquakes, pulsars, all sorts of things. Systems behaviour can be very interesting. Creating systems, open systems with many interacting parts, can be complex. Complexity and emergence go hand in hand, so we like to understand how the parts interact to create wholes with emergent properties. Can we create man-made systems with requisite emergent properties? That would potentially give us more bangs per buck. Anyway, nature seems to manage it, so why can't we do it? Let's have a look at a natural whole, a flock of starlings, in this case over Eastbourne Pier in southern England. Does the flock represent a whole extended organism? Does it act as one? Does it think as one? How could that be possible? Nature creates wholes, you and me, flora and fauna, but it also creates social systems comprising many interacting parts, behaving as unified wholes. Consider, for example, the Hymenoptera, the social insects. They create hives, colonies, bivouacs, that's soldier ants, of course. And other creatures create shoals, herds, packs, flocks. Humans create gangs, villages, towns, cities. Do humans behave like social animals? Surely not. Or do they? Why do starlings flock? To create a large moving mass that confuses and deters predators, of course, but how does the flock come about? How does the whole flock suddenly dive without warning into the bushes? How do all the birds know to do this at the same instant? Is there some sort of flock control or even flock intelligence that we can't see and perceive? Honeybees are particularly interesting. They develop complex societies with social structures, air conditioning, undertakers. One particular aspect is, how do they know when to swarm? Well, you can see some of the words there. Let's have a look at a model of it. This simple model shows us how bee populations grow and how swarms occur. First, let's run the model. Turn that noise off. Let's see what's going on. Line 1, the blue line, is the classic logistic curve, or sigmoid, because it's S-shaped. It shows how population grows, at first exponentially, then linearly, finally starting to tail off at a reducing rate as available resources limit further growth. Line 2 runs inverse to the logistic curve, and shows how much each bee will receive of the solitary queen bee's finite supply of the calming pheromone that is shared between all bees to inhibit agitation and swarming. So as the population grows, there is less per bee. Line 3, the violet line, shows the threshold per bee, below which there is insufficient of the queen bee's pheromone per bee to act as a calming agent. At which point, swarm, form a new hive and start the whole process of creating a fresh population of honeybees. And that's nature's systems engineering. Let's just continue the line to show how they would have gone. And you can see the full sigmoid turning out. So the threshold is dropped just before the limiting point of the resources. Now, that's quite smart, isn't it? And that's an evolved way of doing things. Nature's systems engineering about the human body, a superlative model for system designers and systems engineers. The human body has systems and subsystems called organs and so on. And here we have a selection of them. There's the skin, bones, joints, skeletal muscles, alimentary canal, respiratory system, energy management system, reproductive, nervous, sensing, and so on. Question arises, which organ system or organ could you not have and still be viable? Does a human have to be complete to be viable? I'll leave you with that one. Man systems engineering. Man makes purposeful systems. Man has purpose, and technology serves man's purpose. So man plus technology equals purposeful socio-technical system. Man-made systems come in all shapes and sizes, and you can see a list there. Surprisingly, despite their many differences, they all share common aspects, and that makes them all broadly amenable to similar methods for conception, design and creation, unlikely though it may seem, which is where systems engineering comes in. How many purposeful man-made systems can you see in these pictures? That, by the way, is the ship that appears in the film Murder on the Nile. Explaining systems engineering is probably best done by an analogy in the first place. And here is the analogy. You buy an old jigsaw puzzle in a bag. When you fit the pieces together, there is a big hole. Oh dear. How can you solve this problem? Well, fill the space exactly with white card, as is shown. Use the surrounding context to work out what to paint on the white card: objects, lines, colours, fills. Extend the existing jigsaw cuts to create small jigsaw pieces of painted white card, complete the picture, match the context, and hence solve the problem. Like that. Systems engineering works in an analogous manner. It explores and understands the whole problem. It conceives the whole solution. It synthesizes the whole solution from interacting parts, so that the new whole works with optimum effectiveness in its operational environment to solve the problem that prompted its creation. I hope that analogy works for you. So there you have it. Systems engineering, creative, innovative, and great fun too. And there are systems everywhere. So systems engineering is really an important and valuable skill and discipline. Thank you.